Could you hear me? Or okay. Today I'm going to talk about towards type-safe deep learning in Scala. So towards here means it's not that ready yet. Okay. I'm a little bit of self-introduction. I'm Tongfei Chen. I'm a PhD student at Johns Hopkins University. I work on natural language processing, so I use deep learning all the time in Python. So I'm not very happy about that, so that's what I do. So I wonder how many of you have actually done deep learning here? Okay. So just in a nutshell, what is deep learning? It's just a kind of a machine learning technique where we have this core data structure called tensors, or it's just a fancy name for multi-dimensional arrays. It's not the mathematical tensors. So we could have an image represented as a three-dimensional tensor or three-dimensional array where you have three axes. They're width, height, and color channel. So for example, we have an 100 times 100 image. So in memory, it's going to be a multi-dimensional array of 100 times 100 times 3, where the 3 being red, green, and blue, the 3 color channels. Or in natural language processing, we have a sentence here, the cat sat on the mat. Each word is going to be mapped into a fixed length vector. We call the word embedding in natural language processing. So this sentence is going to be represented as a 2D, two-dimensional tensor or matrix where you have two axes. One axis is the word, and the second axis is the embeddings. So deep learning usually, for example, in computer vision, it comprises of this stacked layers of small functions like convolution, rectified linear units, pooling layers, and fully connected layers, softmax, and whatever. So the whole thing is a composition of smaller blocks. And given this huge function, we can learn by existing data. Okay. So deep learning, in its essence, is just function fitting. The easiest case in machine learning could probably be linear regression, where we learn a function that maps m-dimensional vector to an n-dimensional vector, where the function is y hat equals ax plus b, where a is a matrix and b is a vector. This is probably the easiest function fitting problem. And to a more fancy function fitting problem, that's the machine translation, where we train a function that maps a French sentence to an English sentence. That's still a function that we're going to fit. Let's look at a linear regression thing. So this is the function f, where this thing is called a computation graph, where x is the input. It's you do a matrix vector multiplication by the parameter a, and then you add it with the vector b to create y hat. That's the predicted y. That's the function f that we're trying to learn. In this function, this block, we see that we have two parameters, a and b. So this model to fit is composed from smaller building blocks with parameters. In here, it's composed from multiply and plus and add. And we can train it by gradient descent with respect to a loss function, where here the loss function, usually in linear regression, we use this is mean squared loss, or L2 loss, that we minimize the distance between the expected output and the predicted output. That's the y hat and y. So we connect the y hat, the predicted output, to a y that is the actual output, the gold output, to produce a loss. Loss is the distance between these. So we're going to minimize L. So this is a function. So we're going to minimize the values of a and minimize the value of the loss function L, and to get our trained parameters a and b. So this is what basically deep learning is. It's just a function fitter with parameters. So we can take differentiation against. In industry and in academia also, we already have a lot of common deep learning libraries in use. People use TensorFlow from Google, PyTorch from Facebook, MXNet originally from CMU, now it's acquired by Amazon, I think, and there's DyNet from Carnegie Mellon, Caffe2, Chainer, and So people wonder, if you already have so much tools, so why am I doing this? The problem with all of these is it's just in Python. All of this are just the main languages in Python, which I'm just not happy about. Yeah. So let's look at why Python, where in my opinion is not a very good fit for these problems. For example, let's look at an example in TensorFlow. Look at the linear regression problem if I write that in TensorFlow. So first I start with a thing called placeholder. That's the input node in the computation graph. So M is the size of the vector, and this is the internal type. The type is specified this way as a parameter. This is just very strange. And X is going to be a TensorFlow node, and this is X. And now we start with a Y, and this is the gold output Y. So we start with a parameter. It's a TensorFlow called variable, and we initialize with some normal distribution. B is also a variable. And then we start applying our network, AX, just multiply them, and the predicted output is AX plus B, and our loss is the we subtract the predicted output from the real Y, and we do an element Y's square, and then reduce sum. That's the L2 loss. So this program, see, there is just no types, whether it is a input or it's an intermediate result, or it's a matrix, or it's a vector, or this is a scalar variable, this is not a vector, this is not a matrix. So everything in TensorFlow, they belong to the same type called tensor. So we don't know the actual shape or size or the dimensionality of that at compile time. So or in Python, there's just no compile time. So at runtime, you will just fall into various type errors. From my own experiences, when I program Python every day, I run into like type errors every day, spend hours debugging these. This is like a more complex example. This is in PyTorch. This is actually a copy from my own work in school. So variable is just something similar as tensor, an intermediate result. So I was going to specify the types of this tensors in this way. So this is a natural language processing thing. We'll have a batch of sentences. Each sentence has words, and each word has an embedding. So you can see here, we apply this transpose thing after this. What is transpose? It's just swapping the axis 0 and then axis 1. This effectively changes the semantics of the axis of the tensor axis, but this is not reflected in the type. So I have to write something like a comment here to keep me in track of what is axis 0, what is axis 1. So, and here like unsqueeze is to insert a new axis at the index 1. So this actually makes the tensor having one additional dimension, and this is not shown in a type either. So this whole thing, you have to keep track of this, the types of the tensors yourself. And recently there's been a talk in a natural language processing conference that people talk about what is the good software engineering habits for producing these. And one of their habits they encourage that everyone do is to add type annotations after each of these expressions. So this is not ideal. We want the compiler to track them by itself, so we don't need to remember them. So the Pythonic approach, starting from NumPy, everything belongs to one type, tensor ND array, whether it's a vector or matrices, or it's a sequence of vectors, sequence of matrices, or it's an image and video, a word, or sentences. Everything is just a tensor. So how many axes are actually in the tensor? It's just 0 dimensions of scalar, or it's a 1-dimensional vector, 2-dimensional matrix, or higher dimensional? Or what does each axis stand for? We just don't know. So the programmers have to track these by themselves. They have to remember them by heart. So actually, these people who write Python, they can actually do this. I cannot. Yeah, I cannot remember these. I need static types. So So that's the motivation. So I started my own side project that is called Nexus, that's here, that we try to implement a type-safe version of all of these. So our goal of type-safe tensors is we have a tensor of a type like this in Scala. So axis is an axis descriptor that describes the semantics of each axis. So it is a tuple of singleton types. So each axis is going to have a singleton type as its label. So we know what each axis is. And all operations on tensors are statically typed. The result type is known at compile time. IDE can help programmers. If you are operating incompatible tensors, just compilation error, and if you use IntelliJ or things like that, there was going to be an underscore, a wavy underscore underneath your code to show that you have done something wrong. So for example, let's look at these examples. But first, this is image. So this image in the types in this type-safe tensor notation is going to have a type like this. It's a float tensor with 3 dimensions in a tuple with height channel. With height channel are 3 types, are 3 singleton types. They're just a label phantom types. They're not instantiated or anything. Or like a sentence here is going to have a type word float tensor of word and embedding. So we're going to have type safety guarantees on these. Only operations that make sense mathematically are allowed by the compiler. For example, I have a tensor of A and a tensor of A. So if I add them, okay, we can add them. If a tensor of A and tensor of AB, so this is not addable because their shapes do not match. In some languages like R, this is actually doable. They broadcast this to the same shape of this. They copy the tensor of A to the B times to make it the same shape and add it up. I think that's just a very implicit thing underneath, and it's not that's dangerous. And actually, if I am allowed to quote the Zen of Python, explicit is better than implicit. Yeah, but all these people, they're just doing everything implicitly. And for example, I have another 2 vectors, a tensor of A and tensor of B. They're both one-dimensional vectors, but they don't add up. The compiler doesn't allow them because the semantics of the vectors are different. For example, this is a tensor of width, this is a tensor of height. Still, semantically, it doesn't make sense to add them up. So still, this is a compilation failure. Or matrix multiplication. So apply matrix multiplication on 2 vectors. Doesn't make sense, failure. If we apply it on 2 tensors with the same shape, doesn't work. It only works if the second axis of the first tensor is the same as the first axis of the second matrix. Only in this way that this works. Or let's take a look up this thing. This is called a sum pooling or reduced sum. So if I have a 3-dimensional tensor here, I want to sum over the first axis. This is the 0th, first, and second. I sum over these to reduce it down to a 2-dimensional tensor. How would I do this? In TensorFlow, I write tf.reduceSum x dim equals 1. So this points to dim. And in PyTorch, it's called torch.sum x dim equals 1. We don't like these. So for example, I have an x that's of type this. I would write sum along bx. The sum of sum along b is an operator that sums over the axis b. It results in tensor AC. If I do sum along d, it doesn't work because d is not in the list of the axes a, b, c in a tensor x. So this doesn't compile. So how do we actually implement these type safety guarantees in Scala? These are non-trivial type safeties. So we're going to use the type level programming abilities of Scala to do this. First, I'm writing everything as tuples here. Tuples looks better than heterogeneous lists, but underneath everything are heterogeneous lists. I'm just using the shapeless generic and tupler to transform them forward and back. But so we're going to deal with a shape HLists underneath, so we can do type level computation on top. Before we get into how we implement these type safety guarantees, we're first going to look at how we could produce a type-safe computational graph that uses generalized ADTs in Scala. So Professor Ottersky yesterday just introduced the Scala 3 format of enums. So I'm going to use them here in the code. In my code, it's not actually enum, it's a sealed trait and then case classes. But enums looks better. So we have a symbolic of x. That means a symbolic variable of x that's in the computation graph, that its gradient is going to be computed when we do training. So we can have several cases. There's case input of x. That's the placeholder in TensorFlow that we feed something in. There is a parameter of x. A parameter of x has a var here. It's because its value keeps changing at every iteration. It's a mutable state. And we have a implicit val here. It's a grad, means it's differentiable. This tags, this is a type class that says that this is differentiable. It has some operations in here like addition and subtraction that, or like multiply by a scalar or things like that. Very similar to a vector space. We have to have that to do parameter update. Const is a constant, so it's a constant here. And we have apply. Apply nodes are, if we apply a symbolic variable of x using an operator of x to 1, it results in a symbolic variable of y. That's an app node. That's apply of 1, apply 2, op2, and we support up to op3. So this is a expression tree, or like an AST that we use to formulate the computation graph here. So let's look at what is op1. Op1 is a operator or a function from x to y, but that's differentiable. How do we encode this? So op1 has a apply function given a symbolic vector of x results in a symbolic vector of y. What does it do? It just wraps it in an apply node. It just creates a wrapper around that. And we had a forward method and a backward method. This is the forward method that actually computes the value, and the backward, that is this. So we get the gradient of x using the gradient of y and the function itself. For example, this is op2. We have a forward and have a backward 1 and backward 2. So we propagate the gradient to the first input and the second input using these mathematical formulas. You write the implementation of these in these virtual methods. So in forward computation, what we actually are doing is given a symbolic vector, a symbolic variable of a, we try to get the value of a. We compute the value of a. So this is an interpreter. This is a functional interpreter. So with cats, you can write this as this. This is a natural transformation. So it's just interpreting the computation graph. So we start from x. We're given the value of x and y. So we propagate all the way through L using an interpreter to interpret this graph to get results. Or it's a backward computation where we compute the gradient. We start from the last node, that's the loss, because we're taking the gradient of the loss with respect to a and b. So we do it in a backward way. So we backtrack from this graph. So let's introduce a little thing about operators and modules. So operators and modules are both symbolic functions that map symbolic of x to symbolic of y. Operators have forward and backward, so the computation is executed in here itself. But module is, so here, this thing in this gray box can be abstracted as a module. So it has internal structure, and op is like atomic node. But these are both symbolic functions. So now let's introduce the core part of my work is about how can we encode these type safety guarantees in Scala. So these are polymorphic symbolic functions. So as we have just introduced an op_xy, it only applies on one type x. But for example, addition, it applies on images, it applies on sentences, it applies on any matrix with different shapes and whatever. So as long as the two operands share the same shape, they can be added. So how can we abstract over x here? So we do something called poly function. This is very similar to the Shapeless poly one, if you ever use Shapeless. So this looks like this. So a poly function has a ground function that grounds a given type in xy, produces an actual function that operates in x. But poly function itself does not have any type parameters. But how can we ground this to function? We can only ground this if an implicit f can be found. If the compiler can prove that fxy is there, then we can apply this operator on symbolic x to get a symbolic of y. So this is the core thing. So this is very similar to case.aux in Shapeless, if you are familiar with Shapeless. So this signature, we can apply this function on symbolic of x as long as we can find an fxy. So fxy is an arbitrary type level predicate. So this is compiling as proving. So we are proving that this operator can be applied on type x. If that is proved, then we can proceed with compilation. So implicit fxy is found, that is proposition fxy is proven. So we can encode any type constraint we want on type operators into f, because the Scala has a very expressive type system. So let's look at how these things are actually done. This is a polymorphic operator, just something that we can add an implicit not found here on f. So it produces really good compilation error messages. So if you add something that's not the same type, the compiler would report this operator cannot be applied to an argument of type x. So let's look at how it's actually done. So for example, add. So add, we had a type level we have a logical constraint on the type is as long as this x is differentiable, we can take the gradient of x, and then we know that we can add x and x into x. That's the logical constraint we want to impose on the type system. How do we do this? We write an add with an addf. X is grad. We require an implicit that is differentiable. So it returns an f of x, x, x. That is the proof that we can add x and x to result in x. So that's forward. It's x1 plus x2. This add sign here is there because we have grad. And backward, so addition, the backward, the gradient is just 1. So it's just the gradient derived from upstream. So that's backward too. This is add. Let's look at something more interested as matrix multiplication. So we have two matrices that can be multiplied whenever the second axis of the first matrix coincide with the first axis of the second matrix. So what we want to do is we have a tensor type T, R. So is real type tensor K is a type class that says that T is a tensor type over R. R is float or double, or half if we want to do it on a GPU. So for any of these types, we know that we can do a matrix multiplication over TAB and TBC to get a TAC. That's the logical constraint we want to impose on a type system. So we write this. As long as we have T of is real tensor, and we result in a type of TAB to TBC to TAC. And that's forward matrix multiplication, and that's backward computation. That's the loss. Another example would be axis renaming. Sometimes we want to rename an axis. For example, we want to reuse an axis of a tensor for different use. So in X, if there's a dimension called A, we want to change it to B. How do we do this? So for this operator, we want to have a type constraint that is given T as a tensor. It doesn't require to be a real tensor. It could be an int tensor or Boolean tensor or whatever. So if we have an axis of A, if we remove U and add V, it will result in a B. Then we could say that we can rename TA to TB. So we implement a replace.aux. This is something that proves that if I remove U from A and then add V, I got B. So this is something you can write in a shapeless style thing. This is a type level constraint. Or let's look at a sum along axis, this thing. We want to for example, like this is a 3D tensor of ijk. If we want to sum over j, we get ik. So one dimension is just gone. So we want to encode this type level constraint. Is we remove u from a, we get b. So if we sum along ta, along the axis of u, we get tb. So we do this in this way. So we first get the index of u in a, this n, this is the nth type of a is u, and then remove this axis of n to b. So these are all type level operations in Scala. So this index of and remove add are my own additions to Shapeless. In Shapeless HLists, these are not implemented. So let's implement index of. So what is index of? We know that so index of is a type level function that we can use to get the index of a specific type in an HList. So we know that x is the 0th element in x const t. And we know that if x is the ith element in t, then x is the I plus 1th element in h const t. This is a recursive thing. Okay, so we do it in this way. Okay, let's be fast. That's not enough time now. So we're going to do a native C and CUDA integration. Like this. So this is PyTorch. PyTorch uses MKL OpenBlast and CUDA underneath, and then generates a bundled dynamic library that's like dylib or SO in Linux and in Mac. So we generate a bridge to Python. We plan to do the same in Scala. So this is the same thing, but we have a type class over here. So this type class could be implemented with C native things, using a swig or kind of like Java C++ binder. Yeah. So, and we also plan to do, we could also, because Scala runs everywhere, Scala runs on a JVM, so we could use Torch, MXNet, through a bridge to run on using Torch as the underneath implementation in Scala. Or if we do Scala.js, we have TensorFlow.js as the backend. Probably we can also either do Scala native using the raw Torch C code underneath. So, I don't think I have enough time now, so we're going to it's quick. So neural networks, in a lot of natural language processing tasks, they're going to have dynamic structures. So we have a sentence. A sentence is of variable length. So, and in a lot of senses, we do RNN, recurrent neural model on top of that. So this is basically a fold operation or a scan operation in functional jargon. So in this framework, we implement this with a fold or scan instead of like in Python, they just do it with arbitrary functions. Or in a syntactic setting, the cat sat on mat, we know this is the syntactic tree, this is a sentence, this is a noun phrase, verb phrase. We can do this tree catamorphism on top of it to get the something on top. This is the standard model for sentiment analysis in NLP. So, or we could even do neural machine translation. For example, this is a German sentence, Das Haus ist klein. So we do this as a forward and the backward, and then together, and then unfold to get the English translation, the house is small. And this is the end of sentence symbol. So this is a variable architecture, the state-of-the-art seek-to-seek architecture from neural machine translation. This is about like 1,000 lines of code in Python. But if we're doing Scala, we know functional programming. This is a very functional program. This is scan left, scan right, zip width, and this unfold. So, yeah. So this could be actually written like I think we can actually do this. We can write a neural machine translation in less than 20 lines of code in Scala. Yeah, if we have these primitive operations ready. Okay. Is there enough time left? Okay. So there's also this engineering issue of static and dynamic computation graphs. So there are TensorFlow and Caffe and MXNet when they first produce the whole graph and then interpret it. And there's PyTorch, Chainer, and Gluon, where they the graph is while you build your graph, the values of the graph are actually computed. So one of this is eager, and this is completely lazy. You could do that, think of it that way. But this has this problem because I've said before, there are in natural language processing, you have variable lengths. So these things are hard to code in a static graph because every graph is different. So, but this is easier in dynamic graph, but that is not lazy, that's eager. Sometimes we don't like that. So in our setting, we produce a user control evaluation. Could be either strict or eager or lazy, because for every symbolic value we can put a value function in it to get the value out of it. But it requires a interpreter, a computation instance. So whenever there's a computation instance, we can get the value. So we get the value that's strict, or if we don't, it's lazy. So we can have something like this. So this is the architecture. So pass through a layer, a sigmoid activation function, another layer, and a softmax output. So and then we compute the cross entropy of the loss. So given the input and the output, so in this given clause, there's an implicit computation instance. So in this block, we can do loss dot value, but out of this block you cannot. So every computation here is just lazy, and every computation inside this block is going to be strict. So we can switch between these. So it's just like, I think it's a very cool idea. Okay, so to make it fully work, we want to do automatic batching, complete GPU support. I have preliminary GPU support. This garbage collection, because these GPU memories are allocated on the GPU and JVM doesn't know about it. So we have to do manual garbage collection, and probably distributed learning through Spark. So that's my talk. I'm just doing this on my own. This is just my side project. If anyone would join me, I would be happy. Thank you.
Thank you, Tongfei. That's exactly the kind of talk we want to see here, where you're taking something as abstruse as type-level programming and something practical like deep learning and gluing them together. We do have time for questions, so.
Okay.
Are you aware of the TensorFlow for Scala project?
Yes, I'm aware of that.
Is there any way you guys can work together here?
Actually, I have contact with him. We have some correspondence with him, but his idea, his TensorFlow Scala is just complete. It's just a simple wrapper over TensorFlow. Its API is exactly the same as the Python API, so it doesn't have these type-safe tensors. So yeah.
So I understand you're working on like full runtime for
Yes.
this, right? So have you considered like just using some other runtimes, like exporting it to something like Onyx or?
Yeah, that probably could be done. Probably could be done, but I have a problem with deserializing Onyx into my system because mine is typed and Onyx is not. So I'm not sure. I think I can port my thing to Onyx, but I'm not sure how I can do it reversely.
You don't need to. You just write in
Yeah.
the system and then use Onyx for
Probably. Yeah, probably. But right now I'm using Torch as the underlying implementation.
Okay.
Yeah. So I bind the Torch to JVM and cause Torch. Yeah. Okay.
So all of this time check is done in runtime, not in compile time, independent time, right?
All these checks are done at compile time.
Compile time.
Yeah, at runtime, all these type signatures are erased. They're just a tensor underneath. Or is in the Torch case, everything is erased to a long. That's a pointer to the GPU memory. Yeah. Okay.
You said you only run on PyTorch right now?
Torch. So the PyTorch C core. I don't use the PyTorch Python wrapper. Inside PyTorch is a C++ core. I'm using that.
I have a question. So yesterday we saw a talk from the foundation guys in which they were wrapping, in that case, vocal wabbit in Haskell.
Yes.
So in the same memory space using FFI.
Yes.
So it sounds kind of similar in
Yes.
terms of what you're doing with that C core of Torch.
Yes, that's right. And there is also a new project called HaskTorch that wraps Torch in Haskell using the similar things. Yeah. And it's also pretty type safe. Yeah.
Great.
Yeah.
All right. One more question, and then we can.
Yeah, it's really not a technical question, it's more cultural. Most of the data scientists in my team are trained on Python and
That's
we
right.
are so used to Python.
Yeah, that's right.
How do you evangelize and socialize a Scala library? Yeah, that's the challenge that I face every day.
I know. I write Python every day. I feel the pain. So I guess that I guess that people would eventually know that this is I think is a better way to do everything. Yeah.
Okay. Let's thank Tongfei one more time.